Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is satellites and space stations, another application of circular motion to astronomy. I think you're going to enjoy this one as well as the last one. Please take a moment to pause the video just to see where we're at in terms of what we're going to cover in this video, where we are in the unit schedule, and also what the learning goals and success criteria are. So please do that now. Okay, thanks, and you're back. So we're going to dive right into this. We're going to start off by talking about satellites. And when I say the term satellites, I'm talking about any object that's orbiting another one. So think of what you normally think of when you think of the word satellites, maybe a communication satellite or a spy satellite or a weather satellite orbiting Earth. You know, something man-made, something artificial that people have launched up into space. But it also includes natural satellites such as the moon. The moon is Earth's natural satellite. The Earth and all the planets go around the sun. You could think of them as satellites of the sun. So we're talking about objects orbiting other objects. So here we go. We're going to start off with a question in the textbook. It's one of the sample problems. And first we'll solve it. I think you'll see it's actually not that difficult. And then we'll get into some interesting discussion about what's really going on with satellites. So they talk to you about something called the Hubble Space Telescope, the HST. And the Hubble Space Telescope, just to give you some background information, is a telescope that's not particularly large as far as astronomical telescopes go. The big advantage of the HST was that it was designed to be launched into an orbit that would place it above Earth's atmosphere. And if you know anything about astronomy, like even if you don't know much about astronomy, if you've ever looked up on a starry night while you're in the city, you see some stars here and there, but really not much. If you go up north out of the city, like to a cottage, for example, and you look up, you see way more stars than you can see in the city. And this, of course, is due to all the city lights making it hard to see the relatively faint stars. There also tends to be a lot of pollution and haze in a city, and those are particles in the air which can reflect light back down into our eyes at night, the city lights that is, making it hard to really see the faint stars. But if you go out into the countryside, all of a sudden you don't have those city lights. It's much easier to see what's up out in space. So the Hubble Space Telescope takes this principle to the extreme. NASA launched a telescope up above all of Earth's atmosphere, so it had the clearest view of the heavens that anyone had ever seen. Now, there is an interesting story about how the satellite was launched, and to the horror of the astronomers, they found there was actually a problem with it, and now you've got this very expensive telescope that's up in space. How do you go fix it? Well, very interesting physics story about how they fixed it. Check that out, but it's really not the topic of this discussion, so I'll bring us back to Earth, haha, so to speak, and we're going to talk once again about the physics of the orbit that's going on here. They say that the Hubble, now they talk about figure 3, of course, that's in your textbook, Physics 12 by Nelson. I have not included figure 3. What I did is I took a YouTube image, or not a YouTube, a Google Images image of Earth like this. And let's use a little bit of our knowledge about Earth. We know from class that Earth has an orbit, sorry, not an orbit, but rather a radius of about 6,300 kilometers. So I'm going to write that in here, 6,380 kilometers. And the reason I want to write that in is I want to put things in perspective here. It says that the HST orbits about roughly 600 kilometers above the surface of Earth. So if you were to go an additional 600 kilometers, well, you can easily see that that's about 10% of the entire Earth's radius. So if this is the Earth's radius, really we're talking about not much higher up, and boom, there is where this thing called the Hubble Space Telescope is. Now, they tell you that it has a nearly circular orbit, which I will attempt to draw here with my shaky handwriting, which is made harder because it's not easy to draw on a computer tablet, but there we go. There's the orbit, and if I want, I can just designate that this distance in here is 600, well, not 600, it's 598 kilometers according to the question. And they ask you to determine the speed needed by the Hubble telescope to stay in orbit. So let's draw Hubble somewhere along its orbit, somewhere over here where there's less clutter. And let's analyze the forces that are acting on Hubble. Well, of course, the force of gravity between the planet and this telescope is going to matter. However, what other forces are acting? We are up in space. There's little or no friction to speak of. There are no strings attached. There's no tension. There's no normal force. We're not sitting on a surface. In fact, gravity is the only force that's acting on Hubble at this point. So I can draw myself an inward force that I'm going to call gravity, which is due to the Earth pulling on Hubble. Of course, Hubble also pulls on Earth. That's just Newton's third law, the law of action and reaction. So while Hubble gets pulled down toward the center of Earth, Earth gets pulled up toward the center of Hubble, but we're focusing just on Hubble right now. How much is this force? If we knew how much this force was, we could predict what's going on in terms of circular motion. Well, here's a classic mistake that a lot of students make. They will write this: Fg equals mg equals mass of the satellite times 9.8. And right away, they're in trouble. Why are they in trouble? Because 9.8 is only for the surface of Earth, and clearly a satellite is not on the surface of Earth. In fact, it says right in the question, it's 600 kilometers above the surface. So if you're thinking this, then I'm glad we got this out of the way now. This is just plain wrong. That is not the formula to use for the force of gravity. What is the formula to use? Well, it's the more general version of the formula, the one that says any two masses, so mass of Earth and the mass of the satellite. When any two masses are separated by a certain distance, and of course we've got to square that, and you plug into this formula, you get yourself a force. Now, what information do they give us here? Do they tell us the mass of the satellite? No. Do they tell us the mass of Earth? No. Do they tell us the distance between the center of Earth and where the satellite is? Yes. We do know that the distance is going to be Earth's radius, 6380 kilometers, plus 598 kilometers. And of course, as you know, the reason we sub units in is because we have to realize when we're using the wrong units, we have to convert these to meters. So make sure you do that. Okay? That'll give us the denominator. G, of course, we know is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. What else is left? The mass of the satellite is never given, neither is Earth. But if you look in the back of your textbook, or if you look it up online, you will find that the mass of Earth is approximately 5.98 times 10 to the 24 kilograms. This number is easily found. But what about the mass of the satellite? There are many different kinds of satellite. Do we have to go and look up the mass of the Hubble Space Telescope? I guess you could do that. I'm sure you could find it quite easily. But as you're going to see, we don't even need to know this number, and here's why. The force of gravity is causing uniform circular motion, as mentioned in the question. So we're allowed to write Fg equals Fc. And remember, there's three versions of the centripetal force formula, mv squared over r, one with period and one with frequency. What do they want us to use? Blah, 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 blah. They talk about speed, so we're going to use the mv squared over r one. G, mass of Earth, mass of satellite over that distance squared, equals mass. Which mass goes in the mv squared over r? Well, it's the mass of the thing going in a circle, so it's mass of satellite. What about r? Is that the radius of Earth? It looks like it. It's the letter r. But no, remember, r is the distance from the center of rotation, which is the center of Earth here, and the path. So this r is actually the same as d, so I'm just going to put that in there. And of course, ms occurs on both sides of the equation. It's a common factor. It cancels. Anyway, one of the d's here cancels with the d there. And at this point, you can come up with a formula. It's going to have a square root in it for the speed of Hubble as it orbits Earth. And I think you come out with a number of approximately, give or take, 8,000 meters per second, or if you prefer, 8 kilometers per second. Now, since the mass doesn't matter in this analysis, it actually doesn't matter what satellite you put at this height. Any satellite at that height to go in a circle must be going this fast. And so this is a good number to remember because this kind of orbit, which is really close to the Earth's surface, is known as a low Earth or a near Earth orbit. And the reason that's important is because when you're launching things into space, satellites, it's very, very expensive. The higher you need to launch them, the more expensive it gets. So people who design these satellites obviously want to make use of the lowest possible orbit that they can in order to keep costs down. There are other considerations as well, but this is an important one. It takes a lot of energy and money to get higher up. So since low Earth orbit is exemplified by this question, therefore this number that you got here, that's a typical value for the speed of a satellite in low Earth orbit. It doesn't matter if it's like 400 kilometers or 700 kilometers. All you're going to be doing is changing this number by just a little bit, because remember the d here is being added to a number that's probably 10 times the size. So most satellites at this point are going to be going about this fast, which is pretty fast that you've got to be going. I'd like you to take a hop, skip, and a jump over to the PhET website at this point. So if you recall, there is this online simulation site called PhET from the University of Colorado. Under, I believe it's Earth Sciences, you're going to find a simulation called Gravity and Orbits, and I've got it queued up for you. So we're going to have a look at that. Actually, I'll take you to PhET just for a second so you can see where to go. It's right in here. I think you're going to go under, I believe it's Earth Science here, and it might be Earth Science. If it isn't Earth Science, then it's Physics in Motion, and I think it actually might be Physics in Motion. Download it. It's free. It's easy. It's safe for your computer, and here's what it's going to look like. Now this is a lot of fun, so let's play a little bit. You go to this tab where it says Scale, and click on this over here so you can see Earth with a satellite orbiting it. Turn on gravity. Gravity is a good thing. And in terms of the vectors that we want to see, we could see the gravity force, but actually I don't want to see that right now. I just want to see the velocity, which is an important part of uniform circular motion. Click on Path so that we can watch the satellite go. Leave these settings where they are. Actually, in the beginning, on the planet setting, this is where you get to play around with the mass of the central body, or Earth. I dialed it down just a little bit. The satellite mass I didn't change because according to the formula, it doesn't really matter what the mass is. And what you do now is you can actually stretch out and move the velocity vector, but I'm just going to start by seeing what will happen if a satellite is moving tangent to its path at a speed represented by this vector. And I click play, and something bad happens. The satellite crashes into Earth. Why did it crash? Well, think about this. Take an object in your room, preferably not something too heavy, and just toss it across the room. What do you see? It curves and it hits the ground. It's projectile motion, right? Well, this is projectile motion as well. This is a pretty sophisticated projectile. It's a satellite, but if you give an object that is this high above the Earth's surface, if you give it this velocity, it'll crash. Could we get our satellite to not crash? Because that would be nice, I'm sure, from the point of view of the designers of the satellite, as well as the people who want to use it to collect information. Well, sure, we can get it to not crash. Let's try throwing it or launching it faster. So I stretch out the velocity vector. Now let's see what happens. Make a prediction. Pause your video and make a prediction about what you think will happen this time. Okay, and ready, here we go. Not much more happens. It crashes a little bit further than where it did the first time, but let's stretch this velocity vector out a little bit more and watch again. We keep going a little bit further each time we go a little bit faster, but it seems our path keeps curving to the point that it hits the Earth. Let's try this. A little bit further. This is not a good day for launching satellites. Let's try this. Something interesting is starting to happen. As we increase the speed, we start getting further and further around. We're still falling, but we're getting further. In fact, if you think about it, any projectile is falling, the one you throw in your room or the satellite that's launched by NASA. However, if you can throw it fast enough so it actually goes a significant distance horizontally as it falls vertically, at some point the curvature of the Earth begins to be significant. In other words, the Earth curves away from the satellite, delaying the impact. If you go fast enough, right? Sorry, let me just pause this and go back. If you go fast enough, you just might make it around before you hit. And this, my friends, is the concept of a circular orbit. To be going fast enough that even as you fall like a projectile, the surface of the Earth is curving away from you because the Earth is a sphere, and you might just fall around Earth. The idea of falling brings to mind maybe if you've ever gone cliff jumping. That's a lot of fun, cliff jumping into a lake. Another thing that's fun is falling on a ride like Drop Zone at Wonderland. That's the same as if you were to be flung through the air like a projectile. That feeling of weightlessness that you get, that's the feeling that astronomers or astronauts have when they're on board a satellite, such as the International Space Station, or up until recently, the Space Shuttle that NASA launches. They feel like that all the time because they're falling all the time, but they're falling around the curving Earth. Anyway, this is a great simulation to play with. Some of the other things that you can do is you can really lengthen this to see what will happen. Can you predict what will happen if I really lengthen that vector and speed it up? Now the path is no longer a circle. I go very far from the Earth, and I hope we're returning. There we go. And I come back to where I started, and I pick up some speed and get slingshotted around and repeat. Another thing you could try doing is changing the angle. What would happen if I went rapidly away from Earth like this? Can you predict? You'd slow down as Earth pulls you back, and if you weren't really careful about your path, you would crash. So the direction that you end up starting off at and the velocity, the speed that you have, matter. Anyway, play around with this simulation. It's a lot of fun. Change the mass of Earth and see what happens. Change the mass of the space station and see that nothing happens, like I promised you when we looked at this slide over here, and we saw that mass canceled out, the mass of the satellite. Lots of fun. Hope you enjoy that one. So while we're on the topic of the PhET simulation, I have another thing that I'd like you to do, and that is to watch a short video. This is in the unit schedule. The video here is called Artificial Satellites. It's from this site called Tutor Vista. I think what they've done here is a screen recording of a simulation online. It's about 5 minutes long, and it discusses different types of satellites. You'll recognize these geostationary satellites that we talked about in section 3.3, where we talked about the 24-hour orbital period of these kinds of satellites. And they'll also talk about another kind of satellite called the polar satellite. Those are like spy satellites, for example. Very interesting. Make sure you watch that. Okay, getting back to what we were discussing previously, let's now talk about the next idea in today's lesson, the concept of space stations and apparent weight. So before we get to space stations, we're going to talk about something that you're already familiar with from the very last chapter that we did, chapter 2, where we talked about the normal force and how that gives you the feeling of weight. So in your textbook, again, Physics 12 by Nelson, there's a great series of diagrams here. I've cut everything out so you can take a look at it, but it's pretty clear that in figure A, we have a woman standing on a scale. They ask you to consider that the normal force is equal to the gravity force. And when would this happen? Well, if you guessed it's when you're just standing around, you're right. This is your standard grade 11 Fn equals mg kind of thing, kind of situation. Not a problem. Easy to understand. This is when you feel your regular weight. You don't feel any heavier or lighter than normal. Put that in quotes. Imagine if you're in an elevator now, and the elevator is accelerating downward, as indicated by this, but not at a huge rate. Maybe it's accelerating down, it says at less than 9.8. I don't know. Maybe it's accelerating down at 1 meter per second squared. Maybe It's accelerating down, sorry, I was trying to make a question mark there. Maybe it's accelerating down at 2 meters per second squared, something like that, not 9.8. What would happen now? Well, the woman would be accelerating downward. It would mean there's a net force downward on her. So gravity would not have changed because she would not have changed her mass. However, for her to accelerate downward, the net force must be down. A simple analysis would show you that her normal force must have become less. So this is an example where the normal force is less than gravity, as shown down here, and that's why she's accelerating downward. Now, have you ever been in an elevator that accelerated downward? In other words, you got on the top floor and went down. If you were ever in an elevator like the CN Tower elevator, or a really big office tower where the elevators have to be fast because they've got to take a lot of people great distances, you may recall feeling that as you got on the top floor and went down, you suddenly felt lighter. If you were carrying bags, maybe they felt lighter. Maybe you felt your stomach sort of rise up like you do on an amusement park ride. Well, that was the feeling of the normal force becoming less. And this is, if you recall, in chapter 2, this is how we realized, hey, Fn is the feeling of weight. This is what you feel when you feel heavy or light. It's your normal force. Her mass doesn't change from one picture to another, so she's not getting any heavier or any lighter, but her normal force changes, and that's the feeling of weight. So take it a step further. Go on something like drop zone. If you go on drop zone, anyone who's been on that knows that you feel totally weightless on your way down. There is no normal force acting on you. In fact, that's the whole draw. Because you accelerate down at 9.8, your acceleration must be only due to gravity. After all, that's what acceleration due to gravity is. There can be no normal force acting on you if you're accelerating down at 9.8, such as when you're dropped. Well, let's go back a moment. Is this not what happens when you throw a projectile through the air? Is it not experiencing gravity on its own? And if that's the case, isn't that what we have when we launch, let's reset here, when you launch a satellite? It's a projectile. It's the same as you throwing an object through the air. However, it's going really fast and it's really high up and it curves around the planet. That's how you know that astronauts on a satellite such as the space shuttle actually feel the way you do on drop zone, only they feel it all the time. They don't get to get off after a few seconds. Going back, let's take one more look at the final diagram. And this one here asks you to imagine that you are in, sorry, let me read because I actually haven't read this one too much. Let's see, an astronaut in orbit is in free fall, so the reading on the scale is 0. Of course, this is just what I was describing to you a moment ago when we talked about this. So I guess I actually covered two things there at once. So what is the point here? The point is that the normal force is responsible for apparent weight. And I want you to remember that in our next slide. Because what we're going to do here is we're going to build a device designed to be used in space which will create the feeling of weight by mimicking gravity, but it's going to do it through acceleration. Here's how it works. Imagine if in space, where there's often little feeling of gravity because you're either really far from any object that's exerting gravitational forces, or because you're orbiting the Earth and therefore you feel weightless, imagine if we wanted to take a long trip through space. Well, it's a fact that the human body doesn't do too well if it's not exposed to the feeling of gravity. Our bodies have developed over the years to deal with an environment of 9.8 newtons per kilogram. Our heart has a certain strength to pump blood throughout our body against the force of gravity. Our bones have adapted to be able to withstand the downward push of gravity. So have our muscles. When you go into space, and we know this from astronauts who have been in space for long periods of time, the heart weakens, the muscles weaken, even the bones start to get brittle because they don't have to work as hard to withstand the forces on the surface of Earth. And therefore, when people who have been in space for a long time return to Earth, they can actually suffer very debilitating pain in their body because they're suddenly feeling 9.8 newtons per kilogram instead of 0. So one thing that you can do for someone in space is have them exercise a lot to keep up their strength. But wouldn't it be nice if you could actually have the feeling of gravity, the feeling of apparent weight, so that not only would your body stay healthy, but you could eat and sleep and play and work and do all the things you normally do on Earth in a regular 9.8 environment? Well, here's a diagram from your textbook where a proposal for a space station is put forward. It's a cylindrical space station, and as you can see, it rotates along an axis. People work on the inside of the space station by actually standing on the outer rim of it. And all of their workstations are located in along the circular path. What might this resemble in real life? Well, there was a brilliant movie made actually in, I believe it was 1968, not 2001. It was called 2001, A Space Odyssey. It's by Stanley Kubrick, and it is regarded as one of the great all-time movies, especially for science fiction. If you haven't seen it, you should check it out. I've taken 2 images from that movie, again from, it's either from imdb.com or possibly Google Images, but the set that they created for a sample rotating space station, here's what the space station is supposed to look like, and this is the inside of it. You can see the curving of the inner wall there. People would stand here and walk along. You can see 2 people sitting there. There's a guy sitting here. And would they feel that they were walking in a circle? Because this guy here, isn't he going to go upside down or something? Is he going to get up to here and then fall on his head? Well, actually, no. Remember, gravity from Earth is not really an issue here. All that matters are the forces acting on him. What forces are there? He's standing on a surface and he's going in a circle, so there's got to be an unbalanced force and it's got to point toward the center. It's centripetal. It is the normal force because he's on a surface. Is there anything else? Is there gravity? No, there isn't gravity if you're way out in deep space, so that's not a force acting on him. There's no friction, there's no strings, there's no tension. This is the only force there is, period. So we can actually write, for this guy, Fn equals mv squared over r, where r would be the radius of the space station. So from here out to the edge, that would be r. Or you could write 4 pi squared mr over t squared, and you could figure out the rotational period of this rotating space station. How many seconds does it need to take to go around to generate a feeling of a normal force that will be similar to Earth? See, because what we want is we want the normal force to be similar to the one you feel on Earth in order for this guy to feel like he's working on Earth and for his body not to suffer the way often happens to astronomers in a zero-G environment. So what should we do? What is a normal force similar to Earth? Well, it's like this. This is a normal force similar to Earth. Fn equals mg, a grade 11 kind of question. So what we're going to do is we're going to spin this space station in a way that makes Fn equal mg, where g is the value 9.8, because that's what's going to feel like Earth. And this is the physics of a rotating space station. Maybe sometime in the future this is what they'll look like. This one is close to Earth, but it doesn't have to be close to Earth. It could be on the way to another planet, and we just want to have that feeling of weight. I'll show you a movie clip from 2001, A Space Odyssey. This one is also in your unit schedule. It's very brief, but the scene here is of someone who is on a smaller space station. This space station is not near Earth. They're on the way to the planet Jupiter, and if you want to know why, you've got to watch the movie. So here we go. This is the set of the movie, and you have to imagine someone actually walking. It's kind of like you're walking on a treadmill, isn't it? If you think about it, you'd be like one of those hamsters in a cage on a treadmill. Only the hamster in a cage is on Earth. He feels gravity down. You wouldn't be feeling gravity anywhere. You'd be in the middle of space on your way, whoops, let's watch that again, on your way to, say, another planet. Would you ever feel like you were upside down? Never. See, the thing is, no matter where you are around the perimeter or the circumference of the space station, the normal force will always be up above your head toward the center. And is that not what it means or what it feels like on Earth? We know what direction is up and down because the normal force points up. Of course, that's because gravity points down. One other thing to consider, the fact that you're rotating, what is going to give you the feeling of down? If you guessed, well, it's a fictitious force acting opposite the centripetal force. You are right. There is a fictitious force in this frame of reference of the space station. However, in the outside frame of reference, let's say watching this from Earth, there would be no fictitious force because we would see circular motion, acceleration. So let's actually do a question here, and then we'll finish up. You're an astronaut on a rotating space station. By the way, this is in our textbook, Nelson's Physics 12, Sample Problem 2, Section 3.4. Standing on a rotating space station, the inner diameter is 3 kilometers. This would certainly be a very big space station. I don't see them building any spaceships that are this big anytime soon. However, let's pretend just for fun. So they give you they give you the diameter, which means that the radius is going to be 1.5 kilometers. Remember, we want the radius there. You are somewhere on the outer edge of this space station, like you saw on the previous slide. You could be anywhere. And they ask you to draw a free body diagram for your body as you stand on the interior surface. Okay, not a problem. We know that there's a force directed toward the center. We know we're standing on a surface. This force, therefore, is the normal force. However, in what frame of reference does the normal force act? Well, the normal force acts in both, because in both frames of reference, and by both I mean the Earth's inertial frame of reference, and also in the space station, non-inertial, rotating frame of reference. However, in a non-inertial frame of reference, there has to be a fictitious force, which is opposite the centripetal acceleration. So we've got to draw a force going this way. And if you recall, this force, which is called the centrifugal force, it is equal in magnitude to the centripetal force. That's why you would be able to stand still, like this guy here, on the surface of the space station, on the outer wall. You could be in static equilibrium. But someone on Earth would say, no, 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 no. You are going in a circle. Therefore, there is none of this. All right, so make sure you can distinguish between the two free body diagrams. The one I've drawn for you here, just to repeat, this is the free body diagram in the space station frame of reference. In the Earth frame of reference, of course, what we would have is just the guy there with a force called the normal force. And now let's try to solve this question here and then finish up. Determine the speed you would have if your apparent weight is to be equal in magnitude to your earthbound weight. So we want to simulate 9.8 for our space travelers. So we want to simulate little g equals 9.8 meters per second squared, or newtons per kilogram. What are we going to do? The centripetal force equals the normal force. mv squared over r is going to be equal to what the normal force usually is on Earth, which is mg. Doesn't matter how heavy you are, anyone on the surface will feel the same thing. We set g equals to 9.8, and away we go. Given the radius, which I believe they said was 1.5 kilometers, so don't forget to convert to meters, find the speed that you need to spin this thing at. And of course, do it again for frequency, and for, while you're at it, do it for period as well. All right, and that's it, folks. A little bit of space travel, a little bit of satellite orbits, some fun astronomy. Will we one day go to the stars? Well, if we do, we're going to have to do it in some sort of spaceship that lets us feel like we're on Earth, and so maybe this is the wave of the future. Thanks for watching, and I'll see you in class. Bye now.